Hello everybody and welcome to our video today, which is Organic Chemistry, Chapter 11, Spectroscopy. So let's get it right into it. Let me stand on this side so y'all can see. So we have IR spectroscopy, okay, and IR spectroscopy measures the molecular vibrations, okay, which can be seen as a stretch or a bend by having IR light pass through a sample and the absorbance is measured, okay? And so that's one type of spectroscopy. And for the MCAT, the IR peaks that you should know are an OH peak at 3,300 broad. That would be a broad peak. There's a nitrogen-hydrogen peak at 3,300, but this would be a sharp peak. And then you would also have a C double bonded to O, which would be at 1,750 centimeters to the -1, but it would also have a sharp peak. So those right there are a couple of the peaks that you should know for IR spectroscopy for the MCAT. All right, so next we have over here UV spectroscopy. And the UV spectroscopy is studied for compounds with double bonds and lone pairs because it uses conjugation. So, so basically anything that has a conjugation system. So what happens is as the conjugation increases, the wavelength that is absorbed also increases. And the wavelength absorbed is complementary to the color perceived. So again, this is just, important to know for conjugation systems. That is the spectroscopy that they use. Now, finally, we have NMR spectroscopy, which is a little more detailed. But basically, NMR spectroscopy uses the fact that certain nuclei have magnetic moments and align in a magnetic field. And this type of spectroscopy can be used to determine functional groups and just the chemical makeup, and is based around the proton aspect of it. So for example, proton NMR, the number of signals is equal to the number of non-equivalent hydrogens. So free rotation makes a hydrogen equivalent. So for example, if we look at this example here, we have a CCC, chlorine, and some hydrogens, okay? So we have this carbon is attached to 1, 2, 3 hydrogens, right? However, these 3 hydrogens are able to freely rotate, right? These 3. So they're in an equivalent environment. You could look at it that way. They're in an equivalent environment, which means that this would just show up as one signal, okay? Here is our next carbon. It's attached to 1, 2 hydrogens that are able to freely rotate, right? Which means this would be only one signal. These 2 hydrogens would be represented by one signal. And then finally, you have this carbon that is also connected to a hydrogen, and chlorine, but these 2 hydrogens would be able to freely rotate, which means this would be a signal as well. So you have 1, 2, 3 environments where the hydrogens are not able to freely rotate with the ones in the other signals, if that makes sense. So the ones in its own signal, they are able to freely rotate, which makes them equivalent hydrogens, okay? But there are 3 signals here because there are 3 environments of non-equivalent hydrogens. Okay, so that is just looking at the number of signals. And this is just an example peak down here. Just note that the TMS just serves as a, what's the word I'm looking for? Like a standard control peak. Sorry, a reference peak. Yes, the TMS is a reference peak. So if you're supposed to count the number of peaks or the number of signals, just don't count this one. This is just an example. It is not necessarily related to this, right? Because here we would have 3 signals. This graph, we would have 1, 2 signals because this is the reference peak. So this is just an example of the graph. However, if we're looking at another aspect of NMR spectroscopy, we can look at the splitting pattern, which uses the N+1 rule. So what happens here is that is the number of non-equivalent neighbor hydrogens. So we'll look at an example and hopefully it will be more clear. So we have, again, the same molecule we had above, right? So let's look at this middle carbon right here, right? It's attached to 2 hydrogens, right? We had agreed that this would be one signal, that this would show as one signal. But you have to count the number of neighboring hydrogens to this environment. So the orange, both these hydrogens are in the same environment, so they're in the orange, right? But this has 1, 2, 3, 4, 5 hydrogens, neighboring hydrogens, okay? So that means you would have 5, which would be N, plus 1. So it would be 6, okay? So it would be 1, 2, 3, 4, 5 plus 1, okay, which would be 6. And the 6 represents the number of sub-peaks, okay? So you'd be looking here, it would have 6 sub-peaks in that one signal, okay, for this environment right here. So let's look at this second example here. So you have carbon attached to hydrogen, 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 which we agreed would just be one peak, right? And if we count the number of neighboring hydrogens, okay, so directly neighboring, we would just have 1, 2, right? So the number of neighboring hydrogens is 1, 2 plus 1, okay? So that means you would have 3 sub-peaks for this signal, okay? So that's basically the foundation of spectroscopy, and the important things to know. Make sure you know those peaks up there for the IR spectroscopy, as well as how to read a graph and determine the number of signals for NMR spectroscopy. So stay tuned for chapter 12.